So in the previous video, we have discussed on how the coupling, how the cascading of the many stages, amplifier stages can increase the gain. And then we also noticed that the input and output impedance of the every stages will affect the voltage gain. Okay, the voltage gain, the transfer of the voltage from one stage to another stage, and it will also at the end eventually it will affect the output voltage. Okay, so we also have discussed or described what is the cascade. Even cascade connection means that the output of amplifier A is connected to the input of the amplifier B, and this amplifier B is the next stage of that whole system. Okay, so in this slide show how the cascade connection can be made. There are 4 techniques used to couple or connect the output to do the cascade connection. So the first 2 will be discussed in this course. The first one is what we call it capacitor coupling. If you recall back on the chapter 3 and chapter 4 of the single stage BJT and MOSFET amplifier, the input part, the input source and the input port of the amplifier is connected through the capacitor coupling. So this is what we have done in the single stage capacitor coupling. So the capacitor coupling will block the DC, and at the same time it will allow the AC signal. Okay, so this is an important concept that you need to understand. So please refer to the third example in the previous chapter. In the previous chapter, I have shown you the different in terms of the waveform, the output waveform before the capacitor coupling and after the capacitor coupling. So you can see before the capacitor coupling, the waveform will include the DC source because DC source is not removed, and not DC source, DC signal, because the DC signal is not removed. But after the coupling, capacitor coupling, only the AC part will appear as the output waveform. Okay, and then we have the way we do the coupling is the direct coupling. Direct coupling is very simple. We just use the wiring and then connect the output with the input. So this type of coupling will not block the AC, so will allow the DC signal and AC signal. So means that the AC signal, maybe in terms of voltage and the current, DC current, at the first stage will influence the DC parameter of the second stage for the direct coupling. Okay, for the capacitor coupling, the DC parameter or DC voltage, DC current will not affect the second stage because it is isolated due by the capacitor. So direct coupling. Okay, so this class we will focus on the RC coupled amplifier. Okay, this is example of RC coupled amplifier. So this is the amplifier made from 2 stages. So the first stage is stage 1, and this is your the stage 2. So this is a very simple. This is a stage 1. Stage 1 is a BJT common emitter. Stage 2 also a BJT common emitter. Okay, so how the DC analysis can be done? and how AC analysis can be done. Okay, for this chapter, for AC analysis, we will only cover the mid-band analysis only. So the mid-band analysis only. Okay, so how to do the DC and AC? The analysis, the flow of analysis is the same with what we have done in the previous chapters. For example, for the DC analysis, so you need to take note the first DC analysis, we need to remove the capacitor. So we remove the capacitor or we replace with open circuit. So you may notice that if you remove the capacitor, the source component and the load component, you can ignore it, and then you can have a separate circuit for the stage. So the first stage, this is your R1, R2, this is the RC1, RE1. Okay, and then this part is also a separate circuit. This is the R3, R4, RE2, RC2. Okay, so when you, for this RC couple multistage, the DC analysis can be done separately. So it is as if you are doing DC analysis for two bias circuit. Okay, so you are doing DC analysis for two different bias circuit. Okay, so for this RC couple is quite straightforward compared to the direct couple. How about the DC analysis? The DC analysis is for the capacitor replace with the short circuit. So, and then for this one, you can draw the equivalent circuit. So start with the source. Here, this is your VS, and then you have the RS. This is RS, R signal. Okay, now you have the R1 parallel with R2. Here we have the R pi. Okay, RE is bypass, RE1 is bypass. So this is R pi 1. Let's say I put this R pi 1. So this is V pi 1. This is GM1 V pi 1. At the collector, you have the RC1. And it will also have connection to the next stage. At the next stage, we have the parallel of R3 and R4. Okay, and then we also have at the base and emitter, this is R pi 2. Okay, the voltage across the R pi 2 is V pi 2. So here this is GM2 V pi 2. This is your RC2, and then lastly it is connected to the RL. Okay, so this is the stage 1 and this is your stage 2. Okay. So when you in the AC analysis, the output of the component at the output side of the stage 1 will combine with the input side of the stage 2. Okay, so you can see so all the stages cannot be analyzed separately. So you need to consider the component from the stage 2 when you analyze the stage 1. Okay. So this is the redrawn AC equivalent circuit at the mid-band for the multi-stage. So we have RS, RBB1 is R1 parallel with R2, and RBB2 is R3 parallel with R4. So V pi 1 is voltage across the here. This is V pi 1, and this is also a V pi 2. Okay. So the input impedance for this multi-stage is seen from the input here. From the input, you only see the RBB1 and R pi. Okay, as for the output, we will only see the RC2. Only see the RC2. Okay, for the voltage gain, so we can do the analysis for the voltage gain every stage, or voltage gain or total voltage gain. Okay, for example, the voltage gain of first stage AV1. This is the first stage of voltage gain of the first stage. Put here the stage 1, and this is the stage 2. Okay, for the stage 1 AV1, okay, you need to know the definition. AV1 is output for the stage 1. Let's say put V out 1. Okay, this is V out 1 over VI. So the input at this the stage 1 is VI, and this is V out 1. So what is V out 1? What is V out? Sorry, V out 1, not V out, V out 1. So V out 1 is voltage at this point. So you know the current here is negative GM1 V pi 1. So this is negative GM1 V pi 1 times all the resistor here combined. So this is RC1 parallel with RBB2 parallel with R pi. And then this is divided with the V1 here is equal to V pi. Can be cancelled out. You get this one is GM1 RC1 parallel with RBB2 parallel with R pi. Okay. RC1 is Z, the output impedance of Z out the first stage. RBB2 parallel with R pi is the impedance, the input impedance of the second stage. Okay. So for the AV2 is defined by, say this is V out. It's defined by V out over V out 1. So V out here is minus GM2 RC2 parallel with RL. So, and then what is V out? V out 1? Oh, missed the V pi. Sorry, this is V pi 2. GM V pi 2. So, I missed the V pi 2. So, should be minus GM2 V pi 2. And then V out 1 is actually equal to V pi 2. Okay, so that's why you get this equation. Okay. When you calculate the total gain of the multi-stage, you can simply multiply AV1 with AV2.